Okay, so this is Introductory Statistics. Okay, and I have to say, I love statistics. Okay, so I'll just write that here. It's worth for me writing. Okay. This is when I took my Introductory Statistics class as an undergraduate student. It literally changed my life. I was a engineering major. I finished my undergraduate degree in engineering. I worked for a couple of years, but my stats class, I fell in love with statistics. I took many more statistics classes in my undergraduate education, and then I decided to come back to graduate school here at UCLA, and I studied statistics, and now I have my dream job of teaching statistics. So I'm very much excited to teach this class, and I love the subject, and I hope you guys can gain an appreciation for the subject as well. Okay, and so I know many of you have intentions to pursue health sciences or medical school or something along that nature, but if you read journal articles in the future, my hope is that you will not just skip over the analysis section, but you'll actually understand what they're talking about, and perhaps this is an intro class. We're not going to get into all of the complicated methodology that many of these advanced studies use, but you'll at least understand, I think, a lot of the things that they're talking about there. Okay, so that's my hope. So let's talk about statistics, and just so I have a touch screen, but the problem is like if specks of dust show up on your touch screen, you can't like wipe it away without activating things on the screen. Okay, so anyway, so why do we study statistics? Okay, so I would argue that we study statistics to gain a better understanding of the world around us, okay, and this is probably can be said about many subjects that you would study at school, but in particular, statistics allow us, or the subject of statistics allows us to make conclusions from limited data. Okay, hang on, let me just XL13, March 31. Okay, are you guys able to read this okay? You guys in the back were okay? All right. It seems like the projector's a tiny bit fuzzy, but I don't know if there's anything I can do about that. There's no remote control or anything. You can only just turn it on or off. So.
That looks pretty dusty.
Okay. Well, I don't know. All right. Okay. Well, I guess this is what we'll have to deal with, and if I need to write larger, I can write larger too. But okay. So all right. What do we mean by making conclusions from limited data here? Okay. So all right. I'm going to say a few things. Okay. So maybe we start off with a research question. Okay. Okay, and this is something that we want to know the answer to. Okay, and I'm going to use an example from our textbook. Okay, and this is and the question will be, does exposure to E. coli bacteria, E. coli, increase the risk of liver tumors in mice? Okay. All right, and so to answer this question, we would need to quote, the only way we can know this for sure is if we fully understand the mechanisms behind how E. coli affect the body and how all of these different things work. And perhaps we probably, without a great deal of study and whatnot, we probably won't ever fully know all of the mechanisms going on inside a complex organism. Okay? And so to kind of get an idea of this, we can run experiments. Okay? So we probably won't know fully the complex mechanisms at play here. Okay, so to get an idea of our answer, okay, and the way our experiment is going to work is we're going to take a bunch of mice. Some of the mice, so we're going to have, we'll start off with mice and we'll put them into two groups. Okay, some will get exposed to E. coli, and then others will be kept in a germ-free environment. And then at the end of the study, we will see the rate of liver tumors. Okay, so I'm going to just show you the results of our table. Okay, so so what we have is I'm going to just draw a little table here. So this is what. So for whatever reason, when the people did this study, they randomly assigned 13 mice to the E. coli group, and then to the germ-free group, there are 49 mice. Okay, and these developed liver tumors, and some had no tumors. Okay. All right, so out of the 13 in the E. coli group, 8 of them developed liver tumors and 5 did not. 19 in the germ-free environment developed liver tumors and 30 did not. Okay, this is known as a two-way table. Okay, because we are looking at kind of the relationship between two variables, whether E. coli versus germ-free. So we have two variables. One of them is E. coli versus germ-free. And then the other variable will be tumors versus no tumors. Okay, and so so we can turn these into percentages, and we can say, okay, well, the relative percentage would be 8 divided by 13. So I would do 8 divided by 13, and I would get what? 61.5%, or I'll just round off to 62%, which means this would be 38%. And then over here I would do what? 19 divided by 49, and I would get 39% versus 61%. Okay. So far so good with everybody? Okay, and so based on our data, can we say that exposure to E. coli is linked to an increased risk of liver tumors? Okay. And what would you say? Yes, no, maybe? Okay, so we look at this and we say, oh, 62%. Over here, only 39%. 62% of the mice exposed to E. coli developed liver tumors. 39% of the mice exposed in the germ-free, only 39% in the germ-free environment developed liver tumors. And we would say something like, oh, 62% is higher than 39%. So whatever, more, higher risk of liver tumors. Okay, but this I would say is higher risk of tumors. Okay, but this kind of conclusion, I would say, does not take into account random chance. Okay, does not take into account just maybe we got unlucky mice or something. Okay, so a conclusion that just looks at the table directly does not take into account random chance. Okay? Someone could say, well, we looked at a total of 62 mice, okay? And out of those 62 mice, 27 developed liver tumors and 35 did not, okay? So for argument's sake, let's say E. coli and the germ-free environment have no bearing on liver tumors. Okay, let's assume that exposure to E. coli has no effect on whether or not mice will develop liver tumors. Okay. Has no effect. Okay, and instead we will just say 27 out of our 62 mice were just predestined to develop liver tumors. Okay, there was a genetic predisposition. They were going to develop liver tumors no matter what, whether they were in the E. coli environment or the germ-free environment. These 27 mice were going to develop liver tumors, and the E. coli had nothing to do with it. Okay. okay? We're going to just say this for argument's sake, okay? So 27 out of the 62. Develop tumors no matter what. Okay, E. coli had nothing to do with it. Okay, can you buy this so far? Okay, so if we were to just randomly mix up these mice and put 13 of them in group A and 49 in group B, is it possible that just from random chance that in group A, where I picked 13 mice, I happened to get 8 mice that were destined to develop liver tumors? Could something like that just happen from random chance? Yeah, it could, right? So how do we know that the results we see in our data table here were not just a result of random chance? You don't. Okay. So if I were to just randomly select (13) mice, okay, it is possible that out of those 13 mice, 8 of them happen to be the tumor-destined mice. Okay? So, this could so the results of our table could just be a result of random chance, okay? Could just be okay. So does this so far make sense? Okay. So then that argument could be extended to anything, right? How do we know if anything is the result of anything or if it's just a result of random chance? Okay. And that's essentially the question that lies at the heart of statistical inference. Is what we see, could it be just a result of a random chance, a random fluke? Or is it an indication that something is going on? Is it an indication that exposure to E. coli increases the risk of liver tumors? Okay. We have an intuitive sense about certain things, okay? If I told you, I flip a coin 10 times and I get 6 heads, okay, you would not suddenly come to the conclusion that, oh, your coin is biased to favor heads, right? Because getting 6 heads out of 10, that's technically more than what we would expect, right? We're expecting somewhere around 5 and I got 6. You would not say, oh, you have this strange coin, okay? But on the other hand, if I flip the coin 1,000 times and I got 600 heads rather than 500 heads, then you would start to suspect maybe there's something special about this coin, right? Because getting 600 out of 1,000 flips, that seems a lot more strange to us, okay? So to answer this question, we have to learn probability along the way, okay? And probability will then will be able to tell us, okay, by learning probability, we can say whether or not the results of our table are likely to happen from random chance alone, or if they're unlikely to happen from random chance. Okay, so the rules of probability, by studying probability, we will be able to then say whether the data we observe is likely or unlikely to happen. Okay, probability will almost always never say that it's impossible to happen. Okay, because if it could happen, there is a non-zero probability associated with it. But what we can say is that the probability of this happening from random chance alone is really, really, really small. And therefore, I don't think it happened from random chance. And rather, it would be an indication that maybe E. coli is linked to liver tumors. Okay. On the other hand, if it turns out this kind of results happens from random chance alone quite a bit, then we would say, well, maybe the results we got could have been a result of random chance. Okay, and we could actually just do this. We could just take 62 cards, like a deck of cards, but you add 10 of them, so you have 62 cards. And then on one side you would just write tumors, and then so on 27 of them you would write tumors, and then the others you'd say no tumors. And then you just shuffle them and you deal 13 out into a pile. And then you look at that pile of 13 and say, well, how often do I get eight mice with tumors? Okay, and you can do this over and over and over and over again to get an idea of how likely this is to happen. Okay, now you could do it with cards. We can do it with a computer simulation, so it's a lot faster, or we can learn the rules of probability to do it. Yes?
You were saying if it's linked to versus it causes.
Okay, that's like a whole nother question that I will address later today. Okay, but yes. Okay, so the results could just be the result of random chance. Okay, so in statistics, we will learn probability. Okay, and probability will be able to tell us how likely or unlikely how likely or unlikely our data is. Am I writing that correctly? Okay, how likely or unlikely our results are. I guess that's fine. Okay. Okay. And that probability will then give us insight as to whether or not we can believe it was a result of random chance alone, or if we should believe that it was not a result of random chance. Okay. Okay. All right, and so that's kind of where we are headed in the course in terms of the stuff that we are going to encounter. Okay, so let me just want to make sure you guys have this written down, and then I'll flip to the next slide. So I'm going to just kind of give you a course overview. So we're going to start off with just kind of big picture concepts. And from big picture concepts, we'll move on to descriptive statistics. Okay, and descriptive statistics, we'll learn things like, these are like summary statistics, like the mean and standard deviation, etc. Okay, and then we're going to kind of take a little break and thematically move over to talking about probability. And then after discussing probability, we'll have probability distributions. So this will give us, the probability of what we call random variables, okay? So this is just rules for calculating how likely or unlikely events are for okay, and then probability distributions will be kind of probability rules applied to variables. Okay, and then after we learn probability distributions, we'll learn about sampling distributions. Okay, and so sampling distributions basically are probability distributions of summary statistics. Okay. And then so we'll take our understanding of summary sampling distributions along with descriptive statistics, and these two come together for statistical inference. Okay, and so statistical inference is all about the data that we observed, okay, as expressed by a summary statistic, okay, is our data likely or unlikely to occur, okay? And so this takes us into statistical inference, and so I would say this gets us up to like the midterm exam. After the midterm exam, where we are headed, it will be just an assortment of statistical tests, okay? So this idea of statistical inference can be applied to many different situations and scenarios, and we have a statistical test that's appropriate for this kind of data, a statistical test appropriate for another kind of data or another kind of scenario. And so after the midterm exam, we will focus on an assortment of statistical tests that that we can use. Okay, so this will be
what would be examples of those?
all right, so let me just write this down. Examples of statistical tests. We will have, I'll just list up. Okay, so we have the t-test, the chi-squared test, the Wilcoxon test. I don't know. These are just all different tests. So you don't have to write these down, okay? One-way ANOVA. I don't know. Correlation test, etc., etc., etc. Okay, so we'll have just kind of an assortment, and this is, it's an introductory class. So if you were to study statistics, we're just kind of skimming the surface of, some of these broad topics and ideas. But I'm pretty proud of the amount of stuff we'll cover in the course, and I think it'll be useful for you guys. Okay, so I'd say after the midterm, it's really just going to be an assortment of statistical tests, and the final exam will cover all of these different things here. Okay. All right. Okay, so let's talk some of these big picture things. Okay. And so we'll say we'll start with types of data and evidence. Okay. So there's anecdotal evidence. Okay. And so anecdotal evidence, these would be like stories or personal experiences, or customer testimonials. These are okay. These are bits and pieces of things. Okay, and I'm not discrediting any of these experiences or what people have to say. Okay. However, from a statistical standpoint, we cannot really do anything with anecdotal evidence. Okay, we can't use it and analyze it in a meaningful way. Okay, so from a statistical standpoint, we cannot use anecdotal evidence for analysis. Again, this is not to discredit people's personal experiences and what happened, but from a statistical standpoint, we can't really do anything with it. Okay, so so things that we can use for statistical analysis would be data from observational studies and from controlled experiments. So I'll talk about observational studies first, and then I'll talk about experiments. Okay, so with an observational study, we observe our subjects or participants. Okay. We try not to interfere with the subjects, other than taking measurements. Okay, and often we try to record as many pieces of information related to the outcome as possible. I don't know, just many pieces of information. Okay, so if anything could be related to whatever outcome we're studying, so if you want to know what things are linked to high blood pressure. Okay, we would try to record as many bits and pieces of information as we can. Okay. At the end of an observational study, all we can say is that there's an association say that there is an association between the outcome and certain variables. Okay, we cannot say that a particular variable causes a particular outcome. Okay, there could be what we call confounding variables. All right, so silly example, if we were to look at households across the United States and we look at number of appliances in the home, so this would be things like washer and dryer and blender and TV and things like that. Okay, so if we look at the number of appliances in the home and children's performance in school, we would see a link. We would see the more appliances you have in the house, the better, generally the better performance in school performance of the child. Okay. Does that mean purchasing an additional blender will make your child perform better in school? No. What's going on there? Affluence. Okay, so we might say, okay, so we'll say something like, okay, the confounding variable is affluence or income or something like that, which has been shown also, which is widely understood to also be associated with better or worse educational performance or school performance. But would throwing money at a family suddenly make their children do better either? No, it's much more complicated, right? We don't know exactly how things work. Perhaps what affluence, I don't know. Affluence maybe means that the parents don't have to work 2 jobs and more time can be spent with the child at home. I don't know. It's complicated and sometimes it's tempting just to say this thing is caused or linked or whatever, but all we can say is that there's an association. Okay, and that's what we have with observational studies. Okay, but finding links and associations is still very useful, even if we can't say that one thing causes another. Okay, if you're trying to figure out solutions to problems, it's nice to know exactly what causes another thing, but the world is complicated, okay, and we might not be able to figure out all of the causes, okay. So on the other hand, we have experiments. Or perhaps controlled experiments. Controlled, is that only one L? I don't know. 2 L's, okay. Just looked funny for a second. Okay, this I'm not very good at spelling, and this is like was it on How I Met Your Mother where he's like writing his name on the board and he's not sure. Like this is my daily life here. As I'm writing things up on the screen, I'm like, oh gosh, am I spelling this correctly or not? So I apologize for any spelling mistakes I make. Please don't hold that against me. Okay, so we have experiments, and so on the other hand, with experiments, the researcher, I should say, assigns treatment conditions to the participants. Okay? And the researcher tries to control, I'll say ideally, controls as many aspects of variation as possible. Okay, so this might be best explained with an example. So for example, perhaps we wish to know if a medication is effective in treating high blood pressure. Okay. I should say high blood pressure. Okay, well, there are many factors that go into determining someone's blood pressure, okay? Their age, their weight, their diet, their amount of exercise, even their gender and race and their occupation and all of these things, amount of stress they have in a day. All of these things could go into affecting someone's blood pressure. And so with an experiment, ideally, you can create sets of identical conditions for everybody. Okay, so all of your participants, I mean, this would be rather weird if this were the case, but your participants would be as similar to each other as possible, and all of their conditions applied to them, their living situations and everything, would be identical too. You'd give them all the same diet, you'd give them all the same exercise regimen, give them all the same this and that. And the only difference would be that in one group they get the actual drug, and then the other group they get the placebo. Okay? And then at the end of your study, if you notice that there's a difference between one group and the other, that difference in blood pressure can be attributed to the fact that this group got the treatment and this group got the placebo. Okay? On the other hand, if you didn't design your study properly, and like this would be a terrible way to set up an experiment, but let's say you just mixed everything up or whatever, or even worse, you put all of the men in group 1 and all of the women in group 2. Okay? And then you gave the men the treatment, the actual drug, and you gave all of the women the placebo. Okay? If at the end of the study you see that there's a difference between this group and this group, you won't know if the difference is because this group was men or if it was because this group got the medication. Okay? So that would be a terribly designed study where you can't tell if the difference is because of the difference in treatment or the difference is because demographic differences between the groups. Okay, so in an experiment, ideally you could control everything and make sure the only difference was that one group got the treatment and the other group got a different treatment or different, placebo or something like that. Okay. Okay, so ideally we can create identical conditions for everyone. For all participants. With the exception of the treatment versus placebo or control group. Okay. Any difference observed in the end attributed to the different treatments. Okay. And not, other factors. So with an experiment, we can make cause and effect conclusions. Okay, if the data support it, right? Yes, question.
Could the other factors also be considered confounding factors?
Yes. So in experimental design, you are trying to eliminate confounding factors. You're trying to assign your treatments in such a way that there won't be confounding factors. Okay? But if you can't eliminate them, then they remain. Okay. And so we'll talk about this briefly in like chapter 11 when we talk about ANOVA and how there's blocked designs to try to control for these other confounding factors. But we're going to just kind of say that that this happens, okay? And so with experiments, in order to try to keep things identical across the board, we use placebos and blinding, okay? Because it is known that if you tell someone they're getting a medication, their brain plays tricks on them, and they're gonna feel better whether or not the medication is actually effective, okay? And the same, and with double blinding, you sometimes we have things that are very easily measurable, right? Like someone's weight, they step on a scale and it tells them their weight, okay? There's no trickery there, okay? But then other things requires a professional or someone to do an evaluation, right? So if is someone depressed, they have to see a psychologist or a doctor or something. And there's no machine that you stick your head in and it says, oh, you are suffering depression, okay? They ask you a series of questions. They ask you, how do you feel about this and that? And then, there's kind of a checklist, and then they make an evaluation on whether or not you're facing depression. And so sometimes if someone has to make an evaluation, we don't want the person making the evaluation to know whether or not you are receiving placebo or the drug 1 or drug 2 or something like that. So in that case, we want to keep both the patient and the person making evaluations unaware of which treatment is being used. And so those are, you got terms like placebo and double blind and things like that. placebo and double blind, etc. Okay. And so again, you would only use a placebo in an experiment, okay? Because with an observational study, you're just letting people live their lives, and you're not trying to control these things, and so there's no sense in having that. Okay. We should talk about kind of this idea of, in statistics, so at the beginning I think I said in statistics we make conclusions from limited data. Okay, and so sometimes we have a question, a research question, and the answer to the research question can only definitively be answered if we study every single person relevant to the research question, okay? For example, we might want to know, what is the life expectancy of a person in the United States right now, or something like that, okay? And the only way, and this is actually an impossible question to answer, but to get a definitive answer, because it would require that we know exactly when someone will die, and we need to know it for every single person, and then we would then average all of those values to get the current average life expectancy, which is just not possible, okay? So, whatever research question we have, there's a group called the population, okay? So with any research question, okay, we have a population, and the population would be everyone that is relevant to answering our research question, okay? Okay. What is the average income in the United States? To answer this, we would need to know every single person's income in the United States. Every single person in the United States, we would need to know their income, and then we would average all of those values, and that would give us the value of the average income in the United States, okay? But there's just too many people for us to survey, okay? So the population is too big. The population is almost always too big for us to observe directly. Okay. If we do try to observe the population directly, that's called a census, okay? Okay, censuses are very expensive. We have a population census once every 10 years, and we also have an election census every 4 years, okay? And to see who people want, in elected positions and things like that. But they're very costly to do, and so, unless you're the government with large resources available to you, you can't really do direct studies on the population. Okay, so because it's too big, so instead of studying the population, okay, we will often select a sample. Often select a sample, okay, and we will study the sample. We will select a sample and study that. Okay, and based on what we see in the sample, we then make conclusions about the population. And so in this picture we have the population, again, too big for direct study. Okay, and so from the population we're just taking a tiny little piece, okay, this tiny little piece, and we're going to look at it closely. So this is what we look at. All right, so we study and observe our sample. Observe the sample. Okay, and based on what we see in the sample, we then do statistical inference. Which is all about, kind of make conclusions about the population based on what we see in the sample. Give you a second to get all this written down. Okay, so far so good? All right, and so in order for our conclusions about the population to be valid, our sample must be representative of the population. So one method that should give us representative samples that should but is not guaranteed to do so. Is simple random sampling. Or SRS. Okay, and so for simple random sampling, okay, we start with a sampling frame. Okay, and the sampling frame is ideally a list of every person or everything in the population. Okay, so ideally, of everyone. In the population, okay? This is actually very difficult to do. Okay, because if we think, if I said I want a list of everyone in Los Angeles, in the city of Los Angeles. Is there any way for us to do this?
Not 100%.
Yeah, not 100%. Okay. I mean, what would even be a good method to get a list of everyone in Los Angeles? Yeah, census data that's already 6 years old, because I think in the last 6 years a lot of people have moved here and a lot of people have moved away, a lot of people have been born, a lot of people have died. And I don't know if the government will even release that information directly because of privacy rules, and then there's the phone book, but that's only people who want to be listed in the phone book. And probably none of you are listed in the phone book, maybe. There's Facebook, which is kind of taking the place of phone books today, but not everyone's on Facebook, and I don't know if it'll tell you if you're in LA, and so I don't know, it's hard, okay? So if your sampling frame, the list that's supposed to be everyone, is deficient, then your samples will be deficient in the same way. Okay, so if the Census Bureau has a difficult time finding people without permanent addresses, right? So homeless people or just other people with non-traditional living situations aren't always counted in the U.S. Census. And so even if we were to get the census data, it will have certain deficiencies, and so any sample that's based on that data will have the same deficiencies as well. So anyway, so this is very difficult. As far as this class goes, though, almost all of our examples and problems will say we have a random sample of this, okay, and that's because the mathematical theory behind our statistical tests relies on this assumption that it was obtained randomly, okay? But the truth is in real life it's very difficult to pull off a simple random sample, and so yeah, I don't know. It's hard. Okay? But yeah. And so you have trusted organizations that have devoted a lot of time and a lot of energy into trying to get representative samples. So organizations like Gallup and Pew Research, and they're the ones who are responsible for releasing these kind of public opinion polls on, like, how does America feel about whatever, and they say, 63% of Americans feel this way about this issue. they're trying to get representative samples, okay? Because if they didn't do a good job there, that number 63% of Americans feel this way is useless, right? You know, if they only talk to their friends and say like, hey, how do you feel about this? You know, it might be like 100% of my, you know, 100% of people think I'm awesome or something. You know, like that's not going to be useful. Okay, so you know but anyway, so we start with a sampling frame. Okay, and then all we do is just we select individuals one by one. At random from the sampling frame. Okay, and this makes so all people in the sampling frame have an equal chance of being selected. And all possible samples have an equal chance of being selected. Okay. And what I mean by all possible samples, that means you know, you can think of a lotto ticket, okay? And the way so lottery numbers are drawn using simple random sampling, right? There's, I don't know, let's say there's 60 numbers. I have no idea, okay? 60 numbers, and then you just draw them one by one out of the tank, okay? And what this does is that makes every single number has an equal chance of being selected, and every single possible sample, or every single possible combination of numbers has an equal chance of being selected. So the ticket 13, 18, 52, I don't know, 37, 25 has the same exact chance of being selected as 1, 2, 3, 4, 5, 6. Okay, so they all have the same probability, and that's just a property of simple random sampling there. Okay, there are other sampling methods that the book talks about. And I'll leave it to you in your reading. So from the reading, there is stratified sampling and cluster sampling. And these are, you know, non-random methods, non-simple random sampling methods that try to get a simple random, I mean not simple, try to get a representative sample, which is often used. Okay, so why don't we take a break here, 10 minutes, and then we'll come back and we'll get into Chapter 2, which is about descriptive statistics.